The last section in Chapter 7, we will talk about some arithmetic calculation, but we will direct to using the ASCII value to do the calculation. So that will affect by the unpacked decimal arithmetic or packed decimal arithmetic. So we will show in two videos. The first video, we will talk about how to using the unpack decimal arithmetic. So there are 4 different instructions. We will introduce about that. So the second video, we will talk about what are the packed decimal integer. So then we have 2 instructions to talk about. So the first thing, let's talk about how the ASCII value will do the calculation. So we talked about before, the CPU calculates always in binary number. So that's why here we say when they read the number, even they are decimal number or hexadecimal, but they all display in the binary bit. So for example, before when we see the console on the screen, so we ask you to enter the first number. So on keyboard, actually you see, on keyboard actually you type 5432. So then this value, before we will think about this 5432, actually we will read one by one. So then from each ASCII value, we convert to the binary number. Then we calculate the binary number. On the other hand, you read 5432 in the ASCII value, but you need to find a way to convert that to become 5432. So then you add 3165 in the binary. So after you got that binary number, then you convert the binary back to the ASCII value to display. So that's the logic we talked about before. When we read from the user input, actually our compiler will find a way to convert the user input into a value, a double value or integer to save that, and they will save in binary. However, have you ever think about when we read from the user input, how about I don't convert to anything? Instead, convert to the binary. Can I just using the ASCII value to do the calculation? Then result will be the same. Can we do that? So that's why right here we show you have 2 options to do that, to calculate and display. Before, in the high-level language or what we do the assembly language, we only consider the first option. You always have the binary calculation, then you convert and display in ASCII. So that's why you need to do the encoding and decoding. But now we will show you the other way in the assembly language they will do. So actually when you read the 5432, we just still consider they are 5432 when we convert to the ASCII. So then we direct using the ASCII to do the calculation. We will see how can we do that. The first thing you need to understand, after you try to read from the user input, the user input actually you type the number. We just say here, we say the user type 5678. When you read from the keyboard one by one, you will convert this 5 as the ASCII value, right? So the same thing, 6, 7, and 8. So then let's see the ASCII value, the nature for the ASCII value. For the numbers 0 to 9, actually their ASCII value in the hexadecimal, they are from 30 to 39. On the other hand here, my each box, 35, actually that means 1 byte. But I display in hex. Did you remember hex actually mean you have 1 digit in the hex equivalent to 4 bits in binary. So that's why here my each space, they mean they are 1 byte. So when you have 5, 6, 7, 8, you just convert become 35, 36, 37, and 38. Right? So that's why, because the nature for the ASCII value have that in the each byte. So that's why this one we call the binary coded decimal integer. Actually, they're using the 4 binary bit to present each decimal digit. Like earlier we said, you have 5, 6, 7, 8, right? So when we read, actually they are 35, 36, 37, 38 in ASCII value. But how about we only consider the lower 4 bit? So actually that's easy to do that, because if I want to clear the first 4 bits, so that's a 3. I just can easily to clear that, right? So I can either clear or only consider the last 4 bits. So then I do the calculation. So after we finish the calculation, depends on you want to display in the ASCII or you want them from ASCII to only have the last 4 bits. So you can either do the OR 30 to set the higher 4 bits, or you can do the AND 0 and 1, so to clear the higher 4 bits. So this one is we call the unpacked BCD, unpacked decimal number. So that's the nature, we only consider the last 4 bits. Okay, so please, because the nature from the ASCII value for the 0 to 9, how we convert to the ASCII value, you can see actually the lower 4 bits can really represent the value in the binary. So that's why here we will introduce 4 different operations. Those operations is related to the addition, subtraction, multiplication, division. They all have is they will do the ASCII adjust after the addition. So actually those instruction, they will according to the different operation, they will do the ASCII adjust. So the first one we call AAA. So this one is ASCII adjust after addition. So on the other hand is we do the addition first. So then we will adjust that value. So this one, they will adjust your binary result from your ADD or ADC. So that's why the first thing we are assume you have AL contain a binary number. They are using by adding 2 ASCII digits. So after you add these 2 ASCII digits, so then we're using the AAA instruction to convert that AL into 2 unpacked decimal digits. So they will store in the AH and AL. So that's mean here is we do the addition ADD or ADC. So then you work on 2 ASCII digits. But after you done, so then you will using the AAA. So after the AAA, they will convert this AL into 2 byte value in the ASCII. So we see what that means. This one like me here. So for example, I want to add 8 and 2. You can see here I do the single quote. That means I want to add the letter 8 with 2. So then at the end, I want to display the result is 10. Can I do that? Yes, with the AAA. So what you will do is you just do the regular addition. You just move your letter 8 to AL. So then I just add 2 to AL. Can I do that? Yes, you can. They just convert this 8 in the ASCII value. So that's 38H. So then this 2 is 32H. So after you add these 2 together, actually they are 6A. So incorrect, right? Right, because that's incorrect. That's why we need this AAA. So this AAA instruction, they will convert your AL already at 2 ASCII value. So then after your AAA instruction, they will put the value into AX. That means AH and AL. Each one contain 1 byte in the ASCII value. So that's me, you see here, after you got that right, so then they will adjust that become AX become 1 and 0. So this 1 and 0 actually they will convert. You can easily to do the OR to convert these two become 31 and 30. So that's why you have your result is 10. So on the other hand, that's mean your AAA instruction is convert to correct earlier your ASCII value addition. So then they make them correct into the 2-digit into the AH and the AL. But it's not enough because they only save that's in the unpacked decimal digit. So that's why each unpacked decimal digit needs to OR each one with 30. So that's why they will display correctly in the ASCII. So that's the AAA instruction. So the ASCII adjusts after addition. So the next one actually you have AAS. So that means for any subtraction, you can do the SUB or SBB. So then the same thing like we say, you just see here, if I want to subtract 8 from 9. So that's here, that's clear AH first. So we have AL equal to 9. So we subtract 9 from 8. But remember, they are using the ASCII value. So then after your result, you will see actually they are 0, 1. Okay, but your AAS, they will adjust this value because sometimes this value maybe is not correct. So that's why they will adjust this value correctly. And also they will show you after they done, right? If your carry flag is clear, that means this answer is correct. You can just right away use that. Otherwise, if they are set, you need to do some other operation. So if the carry flag set, that means this one is negative number, but now it's not. So after you're done, you just see the same thing. Your subtraction, because subtraction, one digit subtract each other, definitely they will only still have one digit. So that's why you only need to OR your 30 with your AL. So that's another example to just direct to work on the ASCII value. So the next two actually is the multiplication and the division, but they use a little different. So this one actually, you see, they will do the multiplication perform on the unpacked BCD number. So that's why you see when you multiply, actually you need to multiply with the BCD. It's not direct with ASCII. You need to make them is only if they are ASCII value, you need to clear the higher 4-bit. So here is the 5 multiplied by 6. So that's why the result will be 30, right? But here you see 30 actually they are in the binary value. So the AAM actually is from the binary value to convert them become the ASCII value. So after you're done, you will have your result. The same thing, your AX, you need to OR your each one with 30. So that's why each byte they can display correctly in the ASCII value. So that's the multiplication. So the other one we have is the division. But this division, be careful, is they were using to adjust the unpacked BCD dividend in AX before the division start. So that's why, for example, you have 37 divided by 5. So that's why you see that's 37, right? So each one, they need to be unpacked. So that's why AX is 0307. So they are in the unpacked BCD. So then after they convert that with the AAD, so then their result become 25. So then you can do the division. So then they get the value. So you can move your result AL in the quotient and AH in your remainder.